So I think I'll give you in the 25 minutes I have. Do we really have 25 minutes?
Yeah.
Oh, wow.
On before now.
Yeah. Say 7 lightning talks. How about that? And the slides will have about 40 more minutes of content. So it's really, but luckily you don't have to listen at all because I'm not telling you anything that you can take with the thing. So first lightning talk is the not-so-new trends, what's been going on in the VM, and this is a slide I recycle on these events from JVM OS 2015. What should the VM look like? What has it looked like in the last 20 years? What will it look like 20 years from now? These are my speculations. And also aspirations. It should continue to have a uniform model that unifies objects and interfaces and arrays and primitives in a way that you can work with them all conveniently together and even write generic algorithms over them. That was very imperfect at the beginning of the JVM. The JVM still has this hard division between primitives and objects, but we're working on making that even better. We also, of course, want there to be efficient use of whatever hardware resources are standard, which today means cache blocks of approximately 64 bytes that are prefetched and are weakly ordered relative to each other. So we want to be able to have flatter data. So that's that's something I'll refer to a little bit later. But we want naturally localized data structures that work well in memory and that don't waste a lot of space for housekeeping functions. Of course, we want not only the data to be nice and tight, but the code to be nice and tight. We don't want to run, some kind of a bytecode engine on top with lots of simulation overheads all the way down. We want the VM to drop your code right down, dock it with the metal, and run it as fast as possible. One thing that will be very different, I think, about 20 years from now versus 20 years ago is threads will no longer be the cool thing. Java was an early adopter of threads, and now threads are showing their age. We want something finer grained. We also want interoperability. Java started out as a set-top box and a safe execution environment with security and pointer guarantees. It still is that, but it has a more porous boundary nowadays, and the ceremony required to tie up your native code data with JNI is too much. We want to do better than that. We want the JVM to continue to be broadly useful. We want it to run whatever the modern languages are that are sufficient today, or today might be 20 years from now. We want the JVM to run it. That will probably include C and C++ someday, if they're modern. And then finally, looking back, we want the JVM to continue to be compatible. We want it to run Dusty Dex. And performance, we want to get it, like I said, lower down in the hardware. Whatever the new themes are of 20 years from now, we want the JVM to run them well. So this is our top level goal, is to keep the JVM relevant, applicable, useful, in a word, vibrant. How do we make things vibrant today? Well, today's workloads are pretty cloudy, so we're paying a lot of attention to cloud execution models. We want also, of course, to be compatible with passcode. One of the reasons I think that Java has done so well over the long haul is the commitment, the emphasis, it's a sort of a cultural bias towards compatibility. We want programmers' code to continue running, and we don't want to have them to re-engineer their code every time they recompile it with a new tool chain, C++. So I think that gives us a certain amount of trust in the community, and you can see the sort of glass half empty on that with the JDK9 people worrying about the adoption problems. And I will say we tried really hard, and I think we succeeded well in making the compatibility at a high level with JDK9, where we had to break some things. The JVM has always been fairly reliable. We want it to be more reliable. We want you to trust it, not only with your code, but also with the execution of the data. We want it to be have good tools, and of course, we want open source collaboration. It's the JVM and Java deserve to be something that's developed out in the open and sunshine. What's developed out in the open and sunshine should be the best tool chain and runtime for running code on the planet. to give you the best access to your metal. So that we can basically run the world on Java. You know, I would guess that we run a fair fraction of the world now in Java. Let's keep going and double down. Now, in order to make this work, the VM in particular has a whole ton of technical initiatives that are working. This slide just gives you a snapshot of it. I'm not going to explain it. I'm going to move on and tell you in detail. I trust you will be able to see the slides after the fact. Yes. I'm relying on that. I want to give 6 lightning talks in the very short time I have remaining about some trends that I think are interesting and relatively new in some ways. Java on Java, as exemplified in Project Metropolis, which you've already heard of. Classier primitives, I'll explain that in a second, but that's value types. And richer language support, that's some really interesting little books that we're doing in collaborative, when I say we, I mean we VM nerds, in collaboration with the language nerds, the Brian Getzes. We have fruitful conversations with them between Project Amber and Valhalla. And then, of course, the hardware access in Panama that Mark alluded to is another interesting trend to watch. Concurrency getting more throughputty and granular, better control of the race conditions. That's trend number 5. I think we're going to get better over time. And also, let's scale up to bigger workloads. And there's some really exciting stuff happening in recent months and coming months with some scaling stuff. And all of this, I emphasize, we want it to happen in the sunshine, in the open, with the community. This is something that we want to do collaboratively and quickly in an open source setting. So, trend number 1, Java hosts more of itself. As Mark pointed out, the Graal JIT as an experimental feature is coming to a release near you. This is just the beginning of a series of experiments where we think we will eventually be able to tear ourselves away from that C++ code we love so much and code more in Java. So starting with Graal, the code generator, which is an amazing piece of technology. It has actually a quite long lineage. Much of it has been fostered by some of it in Sun Labs and much of it at Johannes Kepler University in Austria. Deep research. The scales here are really quite impressive. We're looking at 10-ish years of calendar, and just over that period of time, probably hundreds of staff years of engineers working away, many of which are grad students now contributing as professors or researchers. It's been an amazing run, and now we've used Graal as an engine for AOT. That was our first use of Graal in Anger in OpenJDK for the JDK itself. And then also as a candidate in Project Metropolis for replacing the CPJIT as Mark mentioned. So those of you who have experimented with this and worked on it and in hope tried out Graal as a JIT for the future, Chris, there's more to come. Join us. Graal is also good with interpreters and scripting languages, but you'll have to look elsewhere for information about Java. So Project Metropolis is the experimental clone of JDK 11. It's really .jdk, whatever the current JDK is, where we try to make Java implement itself. We bootstrap Java on Java, and we nudge out the C++ code and the assembly code that we've been depending on and replace it by up-level Java code. This requires a certain kind of system Java, which can ably replace C++. We are experimenting with an engine called SVM, Substrate VM, that will give us the ability to shrink down closed Java subsystems into code that is similar to what a C++ compiler would produce. And so that will lead us into the world of being able to take discrete modules from hotspot, maybe even the verifier, and translate them into system Java and replace the C++ code. The big one, of course, is replacing C2. But C2 is just the most optimizing code generator. We also want to be able to replace C1 and the interpreter and various stubs so that we can have a system that is running on one code generator. And of course, last month we discovered what happens if you have too many code generators and then you get a hardware bug that requires them all to be upgraded in parallel. Wouldn't it be nice if we depended on just one code generator? And that's the vision for the Java ecosystem, is to have is to own our own code generation rather than get it from our excellent colleagues at JVM. So tomorrow's reference implementation, more Java on Java. And here's a roadmap. I won't go into details, but we think we can make this work, and we're getting step by step closer. Next lightning talk: how do primitives get classier? Primitives, of course, they're very ghost, but maybe we can add some class to them. The big idea is value types, of course. What is a value type? Well, it's a thing which is like an object, but it's also like an int. It has the good features of both, and mixes them together in a new way that you can't just get with today's object with today's ints. So we want to heal the rift between those primitives. It's always felt like a sort of a necessary but bolted on part of Java. So we make them all more like classes. So the trick here is to distinguish a new type of class called a value class, which is distinct from an object class. And the value class defines things like ints, which have interesting properties I'll tell you very quickly now. The basic slogan is that it codes like a class, but it works like an int. In other words, there is a value class with methods and fields and all this stuff. But in the end, it sort of packages up and scrunches up as this unit of stuff which behaves like an int. I'll tell you in a minute how that's going to behave like an object. This project also requires something really, that's hard, but even harder is doing parametric polymorphism, full polymorphism, generics over not only objects but also values, including primitives. So list of int, yes, that's coming. That's and list of complex, where complex is a user-defined type. Good stuff. This will require, oh my gosh, this is the biggest change we've ever made with bytecodes, and I hope the last big change we ever made. How often do we say that? In any case, it will require huge changes to tools and VMs, and the VM's ready for this. The effect on our source code is that it's probably going to have a similar effect that generics had on our source code, that lambdas had on our source code. In other words, we will have to learn some new things. Here's how I code with value types, but the benefits will, I think, be comparable. Basically, classes are really great for encapsulation, and the system that Java has of interfaces is a really good way to talk about classes without knowing much about their implementations. And we believe we can spread that uniformly to value types as well. And once we grandfather in these primitives as value types, then we will have unity, and we can all seem to play out. So, but if we bring the two sides together, then they both get stronger. Primitives, then, from this point of view, are really just a description kind of a class. I hope someday we will actually write some classes for int, float, boolean, etc., that will show you what their intrinsic state and methods are, and those will just be value classes. And yeah, they'll have a special pleading in the VM, but that won't be what you care about. It's just optimization. Here's a bit of theory about which I'll give you just a taste. Here's what's different about value types from object types, value classes from object classes. The JVM is encouraged and enabled to flatten value types. In other words, if I have a containing type that has a field of complex, it's even complex float, right? And then that complex float components of that will be inlined into the containing object. That's called flattening. And arrays of them will be flattened in a similar way. And the VM isn't required to do this, but it's allowed to and encouraged to. And that allows us to get that cache-friendly data structure that we're after. In order to do that, they must be non-nullable. Null doesn't fit with int. You need 33 bits if you're going to have int or null as a type, right? So 32 bits, that's a non-nullable int. Same for value types. It also has to be identity-free. You can't say which 42. I want to lock this 42. That's not going to be allowed. And so again, they're identity-free. So the VM has to, if the VM does have like little pointers to things holding value payloads, those have to be completely isolated and made invisible to the user. Interesting challenge. So they're flattened. They can be buffered. You can refer to them internally in the VM by pointers, but pointers are never significant to the user. And therefore, you can rebuffer them. You can take the same value and you can buffer it in 2 different places if that's convenient. Or if you see the same value in 2 different places, you can, maybe on a GC pass, deduplicate them. All those things are allowed once identity is removed. Interfaces apply equally to value classes and object classes, which means that interface code can work equally well on values and objects. And object itself is an honorary interface. And that's just a piece of force fit that we have to do in order to make object be a value, a potential value. Basically, object is sort of like comparable or runnable. It's an abstract thing. And that gives us the ability to work immediately with value types in today's erased generics. Although we want to do more. We want to do parametric polymorphism. We want to make generalizations that work across all values, but at the same time, they allow you to compile specialized code that is optimized for the very particulars of a particular value type parameter. So if I say list of complex floats, I want the internal layout of that list not to box each individual complex or each individual float. I want it to have some sort of flat array with real float, imaginary float, real float, imaginary float, all laid out in a small set of cache lines. And that's just the starting point. There's a lot more to say about it. But what we need is something like C++ templates, but more dynamic. And in order to, this mechanism will give us a lot of interesting plays once we get it online. Okay. One way to think about this is, remember that when you're coding generics, your generic types T are in some sense universal, and the T is not the same thing as an object type or an interface type. It's a type parameter type, and there are tricks you can do with the T that you can't do with a plain old interface. Same will be true for these new enhanced generics. This is hard. I won't tell you why, but that's the slide, okay? That's what we get. But the effect of having full parametric polymorphism is you can write generic algorithms over all of your types, not just the object types, all the values, primitive, and reference types. And so you can have you noticed those places like in Java util arrays where there's 7 or 8 different kinds of methods for each different primitive type? And the overloading hides the shame of it. But if you look at the source code, you see that it's bad. So we're going to fix that, right? We're going to be able to parameterize over all those types and have a true generic sort algorithm, for example. I think that'll lead us to better kinds of generics, better kinds of algorithms on arrays. One thing important to note is that we do not intend to expand these things statically. We intend to expand them dynamically and, in a sense, only when needed, although AOT engines will be able to pre-provision templating species if necessary. So I'm going to just skip that last one. Okay, what's a species? I mentioned species. Well, a species is the combination of a template which has formal parameter holes in it with fillings for those holes, causing a particular template to be expanded into species. So that's the basic idea. The VM has to be deep in the game on this, so it requires deep cuts in the VM. The hardest problem is to arrange things so that you don't have to make a million copies for every different species of the code. You want shared code if possible, but when it gets hot, you want to specialize it just like the chip does today. Interesting thing number 3 in my last 6 minutes. So Amber is, as I said, a sort of a handshake between the language designers and the VM. There's a number of little toolkitty things that are really cool. One of them, which is coming in, which is sailing towards 11, is the constant dynamic. That's a part of a trend that I call bootstrap methods everywhere. Bootstrap methods turn out to be a good trick, so we're going to just use them like crazy. We have a bootstrap method at call type, that's easy. A bootstrap method in constant pool, that's Condi. A bootstrap method in a method definition, that doesn't have a cute name, maybe NIMBY, but what it really is a method recipe that expands on use and produces the body of the method. Can you imagine writing your two-string or your serialization boilerplate that way? And then you don't have to load it, you just expand it when you use it. So other pieces are nest mates and sealing. You can sort of watch the Valhalla lists to see the smaller features that we're doing for support of new language stuff. So what this leads us to is a situation where when the language designers tell the VM designers what they need, the VM designers can give them the right generic mechanisms and hooks for new kinds of translation strategies, then the language designers can do really wild new features, but without increasing the bytecode size of their classes. You might have noticed if you're a fan of Scala, that one of the downsides of Scala is that it can't use weirdo VM features under the covers. It has to use standard bytecodes, and as a result, one line of Scala can turn into 20 different class files in your jar, each one of them of a significant size, because of all the little adapter classes that are needed. We think with the bootstrap method trick, we can avoid doing that and make it much more dynamic. Panama has already been discussed, and there's some interesting information here in the slide deck for you, so I'll let you look at that. But the basic idea is BetterJ and I, we want to not work with foreign calls in a heavyweight way. We want foreign code to be brought in as basic blocks right in there with the Java code. So basically you get inline calls to printf and whatever other Unix primitives you want to call. The idea behind making this work is the binder pattern, which knows how to wire up foreign calls to whatever the low-level facilities are in the JVM. And you don't have to pre-compile all of the little stubs and things. You just let the binder create it before you fly. But in essence, it'll give you more direct access to your code and data at the C programming level and even at the assembly level. Speaking of the assembly level, Intel has worked with us to produce a really wonderful proof of concept called the Vector API, where basically you write a Java loop with Java objects, Java interfaces, Java generics, and it compiles right down into AVX code that you could have written in the assembly by yourself. And you would have been proud to write it as an assembly programmer, but it comes from Java. It's great. And we think we can expand that story to platforms beyond Intel, including GPUs. So there's some references for Panama, Loom, awesome, fibers. We need more fiber in our diet. We need fewer dinosaurs to strain over. We want to break up the live parts of our computation into small independent bits that are mounted on a dinosaur thread that gallop along for a millisecond. And then they dismount, and then millions of other fibers are also mounting on the same dinosaur thread over time. So the ultimate goal is to have millions of little concurrent units and just just a small number of server threads. Again, this requires tricky cuts in the JVM interpreter because we need to be able to quickly mount and dismount fiber computations on threads. It's like a user level scheduler for very tiny threadlets. I already explained this, so I'm going to go on, and Ron Kressler is working on this since last year, and he's extending his work on Quasar, which was a user mode above the level of VM. Now he's naturalizing the idea of these interruptible continuations inside the Java VM itself. It uses a low-level concept called continuations, on which you build a high-level concept called fibers, but you could also build generators and other concepts in the future. Finally, our scale will get scalier, and my time is almost out, but it's easy. This is an easy point to make. So we have new pointer-based read barriers in Project Shenandoah, really cool. That's to do with low latency heaps, giant heaps at low latencies. And guess what? Here we are, another project that somehow uncloaked itself, and it uses a different kind of a read barrier. So now we have the fight of the read barriers. Do we use Brooks pointers, or do we use bit-based branches? Oh no, how are we going to decide this? There's too many different technologies floating around, but we can handle this. We're a community. We have some short-term tasks to work with this, besides the individual project work. We want to make sure that we refactor everything that's common to the two projects into one source base and upstream that stuff. So that when you eventually do dock these two different algorithms in, it's not a huge amount of work to have one or the other, or maybe even both, live in the same system. This enables not only coexistence, but also stealing up good ideas from each other, which is a great thing in the community. long-term result, like Mark said, we want to unify low latency PC technology. It's a good experimental, a good bench for experimenting. All right. Fibers also are a scaling technique, which is obvious to all of us. And another technique for scaling is the provision that you get from app CDS and AOT. That's for container scaling. And finally, I can't talk about RACI data because I'm out of time, but look at my JVM Language Summit talk of last year. I think we are in for a new way of looking at managing races in the Java memory model. So, lots of crazy stuff. Can't look at that, but let's go there as a community.